We are very familiar with water, but water is actually very remarkable in the chemical world. Water has a really low molar mass of 18 grams per mole, and yet it's a liquid instead of a gas at room temperature. And if we look at this graph, this compares the boiling point of these substances with the period on the periodic table in which the element X is. So all of these are H2 something, and they're all in group 6A in the periodic table. So here we've got H2TE, that's in group 5. This is H2SE in group 4, H2S in group 3, and H2O in group 2, group 2. Now, there's a trend there with those first three I mentioned, right? And we learned a little bit about graphing, and we would want to draw a line like that, right? There's a trend. What do we expect from water? We expect it to be here, based on the trend with these other ones. Why does H2TE have a higher boiling point than H2S? Boiling point depends on the strength of the intermolecular forces, right? And one of them changes with mass. Remember which one? Dispersion forces, the first one. Dispersion forces, the kind of the floppiness or the polarizability. The larger the electron cloud, the easier the electrons can get pushed around. So tellurium is a larger atom, and so H2TE is a larger molecule. It's more easily polarized, and so its dispersion forces are stronger. So it's going to have a slightly higher boiling point than H2SE or H2S. And if that's the only thing going on, then we expect water to have a boiling point of minus 100 degrees Celsius. That would not work well with life as we know it, would it? If all water was a gas at room temperature. There's an awful lot of water in your body. You wouldn't be functioning if it all turned to gas. But the actual boiling point of water is 100 degrees plus, on the plus side. Why? Because water doesn't just have dispersion forces, and it doesn't just have dipole-dipole forces. It has hydrogen bonding, and hydrogen bonding is much stronger. The water molecules, because of hydrogen bonding, are held together much more strongly than the others in its family. Because sulfur, selenium, and tellurium are all in the same group, the same family in the periodic table, and so they behave in similar ways. They make compounds with the same formulas because they have the same similar electron structure. They have the same number of valence electrons. But water acts very differently because of the hydrogen bonding. Because water is so polar, it also allows many polar and ionic compounds to dissolve in it. Water's the main solvent of living organisms. You have a lot of water in your body, and it's necessary for transporting nutrients and other important compounds throughout your body. Life would be impossible without water. Most places on Earth where you find liquid water, you also find life of some kind or another. Even in Yellowstone, around the geysers where the temperatures are really unusually high, and there's all this sulfur fumes and stuff, and you look at these pools and you're like, ew, nasty, but there's stuff growing in there. It's weird stuff, but it's alive. And this is one of the reasons that astronomers get so excited when they find water. So apparently they recently found some evidence of water on Mars, which makes them, gets their hopes up that maybe there is or was life on Mars. I'm not a big believer in that. I think it's kind of a waste of time and money to be going and searching for life on other planets. But, whatever. To each his own, right? When water freezes, it is weird. Most substances contract upon freezing. They get smaller when they're frozen. But water doesn't. It gets larger. Water in the frozen state, we usually call ice. Ice is less dense than liquid water. Ice cubes float in your drink, right? They always stay on the top. Icebergs float. That tells us that the density of ice is less than the density of water. If the density of the ice was greater, they would sink. Water actually reaches its maximum density at 4 degrees Celsius, just above the freezing point. And this whole idea of water expanding as it freezes is important for lakes. I grew up in Minnesota. Tourism is a big deal there, and fishing is huge. It also gets really cold in the winter and the lakes freeze. But what happens is, as the ice freezes, it floats, and so it stays on top of the lake. And it freezes, it'll freeze thicker and thicker. In some places it freezes thick enough that they actually used to lay railroad tracks across the ice of lakes and run trains back and forth on them in the winter. It saved them a lot of time because they could go straight instead of having to use the regular tracks that wiggled around all the lakes. And that thick layer of ice acts to insulate the rest of the lake and keep it from freezing solid. If ice was more dense, as the ice formed, it would sink to the bottom of the lakes and all the lakes would freeze solid. And that would certainly kill all the fish and most of the other things in there as well. Now, around here we don't get temperatures that cold, but we do get frosts, right? And some plants are susceptible to frosts, especially some of the more ornamental flowers and things. Hostas are really sensitive to frost. And you go out after a frost and they're all just laying limp like cooked lettuce or something. And I was like, what happened to you? Well, what did happen? Well, the cells have water in them. And when the water freezes, it expands and it bursts the cell walls. And that does not do good things to the plant. So the cell walls rupture and those plants die. There are a number of foods that don't freeze well. Have you ever frozen an apple? Apple has a lot of water in it, doesn't it? Or freezing whole oranges. When you thaw them out, they're not the same as they were before. Or even strawberries. They get all mushy because the walls of the cells broke, and that's how they get all mushy. There are some ways around that. Flash freezing is used in industry. If you freeze the fruits and vegetables fast enough, you don't allow the water molecules to arrange into that beautiful geometric pattern that causes them to expand as they freeze. And so you can, by flash freezing something, you can keep all those cell walls from rupturing. And that is the end of that chapter. It always sneaks up on me somehow.